Welcome to The Quantum State, a podcast exploring the latest research and innovation in quantum computing. Join us as we dive into groundbreaking breakthroughs, trends, and news shaping the quantum landscape. Discover the cutting-edge developments pushing the boundaries of computing technology. Through insightful discussions, expert interviews, and in-depth analysis, we unravel the intricate theories and real-world applications driving this transformative field. The Quantum State also offers updates from BTQ, sharing the company's research progress and innovative products at the forefront of quantum computing. So, embark on this mind-bending journey with us as we navigate the realm of quantum computing, witnessing its potential to revolutionize our world. Welcome back to The Quantum State. I'm Anastasia Marchenkova, and I'm joined today by my co-hosts Peter Rohde and Gavin Brennan. Today, we have Hayk Tepanyan, the CTO of BlueQubit. So you are originally from Arctic, Armenia. You moved to Yerevan during your school years and competed in the science Olympiads. Your tech passions led you to Stanford University, where you pursued computer science and statistics. And Stanford, I want to hear all about this. You co-founded a startup, an experience that left a big mark on you despite its closure after a couple years. And after graduating, you joined Google as a software engineer focusing on machine learning infrastructure. And now you're the founder and CTO of BlueQubit, and you're continuing to engage with and mentor the Armenian tech community and especially early stage startups. So thank you so much for joining us today.
Hi, Anastasia. Thanks for inviting me. Happy to be here.
Yeah, so I'd love to hear a little bit more about BlueQubit's new platform and its mission to democratize access to quantum computing.
Yeah, sure. So we launched the MVP of the platform a couple of months ago, and it's basically a very minimalistic website, online tool to let anyone be able to connect to quantum computers and run quantum programs on them. And we think that these kind of platforms are essential for democratizing access to quantum computers. A lot of people think that quantum computing is still like far into the future, and it's only in fantasy movies and scientific sci-fi movies, but it's actually a reality, and there is already a lot of companies building quantum hardware, and BlueQubit is here to provide access and make it easier for people to actually interact with those quantum computers.
Yeah, tell us a little bit more about what really inspired you to start this company.
Yeah, sure. So I'm personally coming from software engineering background. I used to code on regular computers since I was 9. Always been interested in computing. My co-founder, on the other hand, is actually coming from physics background, and he's been doing quantum physics for quite a while now. And when I met him first, a couple, say 8 years ago, I basically learned about quantum physics and quantum computing from him. And it was really captivating and super interesting for me. And ever since, so that was around 2016. And I was a sophomore at college. And ever since, I've been kind of tracking the trends and new developments happening in the quantum industry. And there's this saying that if you think you understand how quantum physics works, then you should think it over, because it's really paradoxical and super unintuitive. And that part is really captivating for me. And quantum computers that are built on these principles of quantum mechanics and quantum physics are truly something like out of this world. And all these things basically pushed me towards learning more and trying to become part of this community. And after following the trends and developments in this industry for a couple of years, last year, me and my co-founder decided that now is like a good time to actually start contributing and doing something ourselves. And that's how we founded BlueQubit. Me personally coming from software engineering background and my co-founder coming from quantum physics background, it was only it was a great synergy to basically found the company in that direction of building quantum software by using existing and upcoming quantum computers. And yeah, that's how BlueQubit came to be.
As an aside, I love the fact that we're now calling it regular computing. Like we have to specify in our field, like, oh, that's the regular side, the classical computing, and these are the quantum computers.
True.
Yeah, there's different names people call it, right? Classical computing. Sometimes I say regular computers, but yeah, we definitely need some terms to differentiate between the two.
And then there's also the hybrid quantum computing systems as well, right? So we're now going to have this range of systems, right? Maybe that's the thing. Instead of the binary, regular, classical, and quantum, we're going to have that's superposition entanglement of all our computers together.
We'll have a continuum of different computing.
Exactly.
Yeah. Yep. All of those are very pretty new terms, but already have a lot of connotation. Like there's actually a company called Quantinuum, and there is a hybrid quantum is like a big thing. A lot of companies are focusing on. But yeah, it's exciting to see how the community is growing, and so does the vocabulary describing the community too.
Yeah, there's a hybrid side. There's the quantum inspired side. There's so many different aspects of it.
Can you talk a little bit about your transition from computer science to quantum computing? Like, I'm just curious what the training was like in, say, the computer science departments, and is it taught at a very abstract level, or do people get into how the systems are designed from the physics side?
So I haven't done much quantum computing at college. I've done computer science and stats, but also taken some linear algebra classes, and I would say like those have been perfect to kind of build that foundation to start getting into quantum computing. I would say like, yeah, basically, if you have the foundational knowledge in linear algebra, math, stats, and some physics, yeah, that's a good way to start to get into quantum computing. I would say it was not so easy at first to kind of get the basics, the bracket notation, the state vector, wave function collapse, all these things, right? It's like I would even say it's like there's this high barrier of entry. It's not like, I don't know, like learn how to do Hello World on Python and you can get your hands on it in a couple of days and start writing programs in a couple of weeks, right? With quantum computing, it's not like learning a new language, right? It's a whole new paradigm. So yeah, it took me actually a couple of months to just head down reading different textbooks. I started with Isaac Chung's the book on quantum computing, which many people think is like the best in business, and then started again doing some hands-on interactive trainings and courses, mainly Qiskit. IBM's Qiskit is a great resource. A lot of people ask me like, how do I get started? How do I learn the basics of quantum computing? I always direct them towards IBM's Qiskit. I feel like they compiled a pretty nice list of easy to get started courses, and yeah, that's of course over the whole journey. My co-founder's help was super important because yeah, I would just bother him day and night with different questions, and he was very patient with me to answer all those questions I had. So yeah, that's how I got into it and then fell in love with it.
So a lot of people in our field come from that sort of background that you described, heavy in physics and maths or engineering, but not all jump on board with the quantum computing bandwagon. And lots of the people who do, they sort of describe having a moment of, aha, this is the way to go. Do you see yourself that way? Was there a moment of realization where you thought, this is what I've got to do?
Actually, that's a great question because I have the perfect answer for that. And I definitely had that aha moment. And if you know, again, from Isaac Chung's book, there is this Alice and Bob experiment describing Bell's inequality. But again, without getting too technical, it's basically thought experiment, more like a scientific experiment that basically shows how quantum computing breaks local realism, which is insane. If you, ever since I've been trying to figure out a way how to kind of explain that experiment without using a lot of technical jargon, and it's actually pretty hard. Like for me, it took like a couple of months to basically build the prerequisites to understand that one page of information. But once you get it and you understand like how in this world there is like things that cannot be explained by intuitive math and statistics, it's basically like rolling a dice that has only numbers 1 to 6 on it, but getting something that's bigger than 6, right? If you put it in like very, very high level, very simplified terms. So it's like totally out of this world what happens in that experiment. And after learning that, I was like, yeah, this is crazy. This is like totally something that a lot of more people need to like understand and see into it. And yeah, I would say that was the aha moment for me.
Yeah, it's funny. In undergrad, that's actually, I think, the first quantum concept I learned because I worked in a quantum telecom lab in undergrad. And still to this day, I've been in the field for so long. And I think about it, if I think about it too hard, I feel like I lose that knowledge and I have to go back and like re-reason again. That like, I know this worked. I've seen the experiments. I've done this experiment. I know this is true, but it takes a few steps to get back there. I mean, with quantum education, it is so interesting. I remember the first day of my undergraduate quantum physics class, they said, okay, remember everything you learned in classical mechanics? Forget all of that. Nothing here applies anymore, and we're going to have to figure it out in a different way. So it's definitely a big leap for people. But there's a lot of interest in software engineers kind of transitioning into quantum computing. So what advice would you offer to someone looking to switch into the field from what you've learned? And what do you think we can do better in teaching quantum to software engineers?
Yeah, that's a great question. Again, a lot of people ask me like, should they do the switch? Should they actually start learning quantum computing? Should they like leave their career as a software engineer? And I would always tell them that it's not the most safe bet. Again, there's still a lot to be learned and uncovered and discovered in quantum computing world. So a lot of people, again, ask me, like, should I go do AI or should I do quantum computing? And I would say, you know, if you want the safe, non-risky path and career growth, you probably should go after AI. But if you like truly, if you looked into quantum and you saw how like amazing, unintuitive and paradoxical it is, and you're actually captivated by it, then yeah, you should just listen to your heart, however cliche that might sound, and just follow your passion.
I guess it's safe as long as we don't run out of GPUs for the AI side, right?
Yeah, yep, that's another one.
Or it gets banned. It's going to be all kind of
yeah. There's yeah, it's like literally a race right now, right? It's not just like in US competitive companies competing against each other, but also on a international level. Yeah, we keep hearing like different regulations coming into effect, and US-China race is like getting heated more and more. So yeah, I don't know. It might even be a good thing for the development of the technology, one might argue, right? Because kind of there is now more pressure to kind of get to build new stuff. When you like read on how like companies or universities in China build 1,000-kilometer long network of quantum communication devices, then yeah, I feel like you're extra motivated to kind of work harder on your project. So.
Can you tell us a little bit about how BlueQubit's platform works and how it makes quantum computing more accessible to researchers and to students?
Yeah, sure. So the current version we have online basically has a couple of resources for different audiences. First, I would mention the free simulator that we have that lets you run quantum programs on it. I can say that, to my knowledge, it has the largest state vector simulator publicly available. It can simulate up to 34 qubits. And it's faster than a lot of its competitor platforms. So I recommend everyone who has large experiments, large simulations to run, to give it a go. It supports Qiskit and Cirq, two major quantum languages out there. And basically, yeah, the way it works is we have a BlueQubit SDK written in Python that you can install. And if you have your quantum programs, your quantum circuits, you add 3 lines of code at the end that basically imports BlueQubit and sends your circuit to our backend. And that's where the simulation happens. So yeah, you don't have to change your code. You don't have to port anything. All you have to do is add these 3 lines of code to move from your laptop to the large simulators and large servers that we have in the cloud. That's one thing. There's also there's a couple of other simulators that we're working on right now. We're working on bringing tensor network simulators, which are getting more and more popularity recently. And there is also the ability to connect to real quantum hardware. Right now, we are supporting Rigetti. Rigetti's Aspen M3 79 qubit quantum hardware. And yeah, we're actually working on adding a couple of more quantum devices as we speak.
The 34 qubit device, well, simulator rather, that you mentioned, that's already quite a hefty number of qubits to do classically. What are the differences or distinctions between your state vector simulator that runs the backend for this compared to the very many other ones out there? This is something that's been around for a long time. Is there any notable distinction?
I would say, first of all, big disclaimer, this simulator is not something that we built from scratch. Under the hood, actually, it's using Google's QSIM library, which is an open source simulating tool. And there is plenty of such simulating libraries out there written in Python, C++, Julia, and other languages. And what we did when we were starting BlueQubit, basically, first of all, we actually, 2 years ago, when I was still learning the fundamentals of quantum computing, I wrote my own simulator. And that was a great experience to learn, again, basics of quantum computation. I highly recommend anyone who's trying to move from software engineering to quantum computing to write their own simulator. It's a great project. And yeah, after that, we started like benchmarking different open source tools out there. And that's how we found this library from Google. And we figured that it actually has the best performance in general, if you try it on different random circuits, QFT, all kinds of different circuits. And we decided that there needs to be like a nice layer on top of this so more people can use it without going through the pain of installing the right software on the right hardware, installing the right libraries, and making sure the whole setup works smoothly. So that's how we built this thin infra layer on top of it. So now you can just add 3 lines of code on top of your Qiskit or Cirq code and just make use of this large 800 gigabyte machine that we have in the server.
I mean, having a high performance and powerful backend like that is crucial to making it work. I guess the other aspect is how it's interfaced with the person who's using it, and that could make or break anything, because it's very difficult to think about how you make a graphical interface or any kind of interface for something that underneath it has so much depth and so much complexity. What do you see as at least in your approach, how do you see that problem as best being solved in a way that covers all bases, novices, experts, specialists, beginners?
Yeah, that's a great question. and definitely not an easy task. We're constantly improving our platform, actually. So in its current form, it offers some minimalistic functionality that we think is good both for students and researchers. So in its current form, it's showing you some visualizations of your circuit, the visualization of the state vector and the results that your circuit produces, things like that. So you also have like a history of all the jobs that you run, so you can always go back and pick something that you run a couple of days or weeks ago and change something and rerun it if you want. So little things like this make the simulator experience more user-friendly. But yeah, having said that, I totally agree with you that when you run these large simulations, there is so much more that one can do to improve the, again, usability of these tools, right? For example, a couple of months ago, we had this a POC, basically proof of concept, where we work with the company to run some large simulations, and we pushed it to a limit of 41 qubits there. So it was pretty large machines there. But with these things, you basically, all you can do with the current tools we have is to kind of kick it off and just wait 10 or 20 hours for it to finish. And if it for some reason stops in the middle of the work, it's really hard to debug a quantum program. I haven't really seen any tools out there that let you kind of debug quantum circuits and see what went wrong in the middle of it. So that's definitely another area that we're looking into, and we might add a couple of other tools to help with that in the future.
Yeah, just a question about, when classical computers started to become commercially available. So, we had like the first Apple, like the Apple II was really the most viable one. And then there was Microsoft products. People were like coming up with all kinds of interesting, ways to sort of do the best they could with these terrible clock speeds and really tightly constrained RAM, storing things on floppy disks. And so like having the limitations of the product actually kind of forced people to become more creative. And I was just wondering if you've experienced that with users or yourself working with your platform. When you're stuck to 34 qubits, have you come up with sort of new approaches that maybe exceed what's known in current research? Has it kind of forced you to become more creative in your approach to quantum programming?
Yeah, that's definitely a part of any large experiment that we run. Specifically with that 41 qubit experiment I mentioned, we did a lot of work to make sure that we do not waste any qubit, basically. And I totally agree with you. When you have these scarce resources, you want to like make most out of every quantum register you have, reuse as much as you can, not waste any qubits. And it's hard to tell. We have like, again, a lot of different techniques for building these circuits, but I don't know if I can say for sure that we have like some groundbreaking new discovery that's not known in the research yet. Yeah, it's not really like that. We don't really look at it that way. Maybe if someone builds a compilation tool, they can come up with such techniques there. But we're not operating on that layer. We're not really building quantum compilation tools. That's a great question to ask. For example, folks at Q-Control, for example, they build, and there is also other companies that help you transform your quantum circuit and make it work best on a given hardware. I would imagine they would need techniques like this to, again, make sure that every program is compiled in the best possible way and makes use of every single qubit in the hardware.
Yeah, something I hear, people comments that aren't in quantum at all. Like, how do you do something like a while loop in quantum computing? Because we don't have that. You can't do it because you can't check your register without collapsing it. So you have to think in a different way.
Yeah, I totally agree. And I would say that's also like area that I think is gonna be maturing more and more in the next few years, where we have like more programming patterns and data structures maybe that are actually specific to quantum. So people do not try to get the analog of for loop or a while loop or an if in quantum, because all of these things are kind of irrelevant in a quantum programming world, right? It's all it's a different paradigm. It all has to do with the phases and the wave functions and the state vectors. So you got to think in those terms, kind of, right? The unitaries and the eigenstates and the eigenvectors. So it's like a whole different terminology too. But I think that people in classical computing, again, the analog of all this low-level terminology is the different gates you have in classical computing, right? And I think that's where the best similarity is. You have classical gates like OR and XOR, all these things, and you have quantum gates. And that's where the analogy between classical computing and quantum computing basically ends. And after that, you start getting into all this. On a classical realm, you have the for loops and while loops and hash maps and arrays and dictionaries and things like that. And in quantum world, it diverges to totally different stuff. But what's the best way to describe that different stuff? Yeah, I feel like we're still in the process of figuring that out. And people talk about like quantum memory, quantum RAM, all these things, which sound cool, but I feel like there's still some long way to go to figure out the best terminology for this.
Yeah, it's definitely a big change in thinking. I actually spent a few years programming classical computers, as we're now calling it, and I remember, well, I always say physicists are good coders, they're not great software engineers, and I wanted to learn that skill. And part of that was changing the way that I was thinking, because physicists tend to code procedurally, right? Because you just go through line by line. This is the algorithm, step 1, step 2, step 3. Again, like Peter mentioned, you can't really go back, right? You can't do those loops. And I had to be kind of retrained to think more functionally. And this is now the other way, right? You have to think in that new way and teach this new paradigm and teach the hello worlds and how do we build those analogies. But it's interesting to me, really, because again, as I mentioned, physicists are taught a little bit different thinking in the programming side. How did your work with your ML side contribute to the development of BlueQubit's platform? That probably brought in a lot of learnings that you had at Google, and how's that helping now with this access and helping people understand quantum?
Yeah, my work at Google was mostly focused on ML infra. So while I was working with ML models, I was mostly working on tools and infrastructure that helps the AI and ML inside Google, especially Google Ads, to move forward. So I would say definitely my skills and my experience there helped me in the process of building the infra at BlueQubit as well. Because again, if you throw away the ML and quantum part, the rest is pretty similar, right? We have like you have some programs that you need to run on large machines, and you to make sure that everything runs smoothly and the user has the best experience when going through these workflows. So definitely, yeah, my skills and experience at Google has been super relevant in that regard. In terms of ML and AI, though, I would say that there is a big push recently, again, that we see in terms of quantum ML. And we actually do have some of our R&D team looking into quantum ML models, like variational circuits and things like that. And yeah, we're actually pretty excited about that. We think that first use cases, it's totally possible that first use cases of quantum computers will come from QML models, because these things are numerical rather than theoretical. It's hard to kind of sit down with a pen and paper and derive what algorithm exactly you can run with a 100-qubit quantum computer. But if you had a 100-qubit quantum computer and you can put it in an ML workflow, the only way to figure out what it can do is to actually run it and go through a bunch of different experiments. Doing that so far with smaller quantum computers and simulators, we actually see a lot of promising results. And we think that numerical experimentation and QML can be very big in the coming years.
I'd be interested in hearing what some of your predictions are, or rather what you're placing a bet on as the future killer application for quantum computing. How do you see quantum computing transforming or influencing a field like finance, one that we hear about quite often? Do you think that it's going to be really transformative or something more modest than that? What's your impression?
Yeah, so it's a great question. In my view, first use cases, like first real quantum advantage. Okay, let's take a step back, right? So first claim of quantum advantage was 2019 by Google, where they did this sampling experiment with random circuits. So they did show quantum advantage, but it was on a problem that's not really used anywhere, right? It's like, you can think of it as a problem theoretically designed specifically to show quantum computers' advantage over regular computers. So next up, I think there's gonna be quantum advantage in a scientific realm, where we show that quantum computers can beat classical computers millions and billions of times on a problem that helps with the some scientific discovery, right? And this still might not have applications in real world, but it's going to be big in the scientific community. And after that, actually, on that note, a lot of people say that we are already in that phase. I would love to hear what you guys think about it, actually, because there's different. There was this IBM paper, for example, right, with 127 qubit, where they basically claimed achieving quantum advantage, but a couple of weeks later, some other researchers came up with tensor network simulators where they say they can achieve a similar result. But from what I understand, the higher modes of this problem, where they run both the quantum computer and tensor network, both of the results are uncertain, and it's hard to check which one is true. So it still is entirely possible that the quantum computer has a more accurate result. But yeah, we're in uncharted territory. It's even hard to kind of check whether or not it's true or not, right? So we're in that gray area right now.
Yeah, this is
after that
conversation.
What's up?
That's a repeating conversation. The issue that people solve these contrived problems, which are almost by design made to demonstrate quantum advantage. But the trouble is, we don't actually have proofs that if you get a result, how do you know that it's correct? And this is an outstanding issue with lots of problems in this class at the moment.
Well, I think the history-making moment will be when a quantum computer solves a problem in NP dramatically faster than a classical computer.
When we get a decision problem where you can verify it and say, yes, it worked.
Yeah, that'll be great. That'll be awesome. I still think that even before then, we will have some sporadic applications here and there, like relying more on numerical approach, like variational circuits, QAUA or VQE type quantum circuits, where you have some optimization. And this might even be, again, a practical application in finance or logistics or transportation, where you have a problem and you're able to do optimization for it more accurately or faster or cheaper with a quantum computer. And then, I'm totally on the same page with you guys. If we solve an NP hard problem with a quantum computer in polynomial time, that'll be awesome.
I think in terms of the simulation, that's also an interesting point. I think one thing we bring up all the time with this podcast and whenever any scientist is talking about is, right now we have a handful of algorithms that we know quantum computers could potentially speed up, right? But until we get them into the hands of actual domain experts, the actual quantum computers, we're not going to know actually how far we can go there. So it's interesting, right? I think a lot of people are disappointed. Oh, this is just a toy problem that is solved, or, someone released a paper, but then someone came out a few weeks later and said, well, we found kind of a similar approach. I almost don't think that's that big of a failure, because a lot of these, I've read it specifically in simulation papers where we've had these kind of toy problems or applications of quantum computing. It works on the simulators, and then that actually is a breakthrough for the industry because it's actually allowed for cost savings in the simulation space. So for me, that's a success because it's actually bringing us closer. And then when we actually have the chip, right, then you can actually run it on those chips. It's going to be even better. But even that, I feel, is a win for the industries in general, because we're talking about industries that are like aerospace, materials, pharmaceuticals, finance, huge industries that spend a lot of money, create a lot of work that they're doing. And I think that's still a win.
Yeah, I totally agree. Aside from just being like an indicator that we're already in this uncharted waters, in this gray area where it's like some 10 years ago, again, nobody could make such a claim. You could like show on your laptop that your laptop is more powerful than whatever computation your quantum computer came up with. But now, yeah, we're in this area where even the largest supercomputer in the world can't make such a claim confidently. And also there is the discovery of quantum inspired algorithms, right? Like, again, you kind of come up with these computations going through the quantum route instead of thinking in the regular algorithm terms. So yeah, there's definitely we're definitely in uncharted territory now.
Just to touch back on Peter was wondering about sort of the applications of quantum computing to the finance sector, because obviously there's a lot of money there. And it could do some good. So where do you think are the key problems where quantum computers could offer some advantage there? You know, we often hear the statement that quantum computers aren't good at processing big data because it takes, it's not efficient to load and extract big data from quantum registers. But are there some particular problems in finance you think that quantum computers really have a good promise?
There is two that come to my mind. We haven't worked too much on those, but again, they're pretty well known in the community: Monte Carlo simulations and portfolio optimizations. These are like vague, generic terms, but I personally think that there's a lot of Monte Carlo simulations being done in the finance industry for derivative price calculation, risk management, all kinds of things. And it's entirely possible some of these applications are the first applications from quantum computers. I totally agree with you with the data loading problem. A lot of research papers you read that describe a quantum algorithm, they would start with let's assume we have the data in a quantum computer, but how do you get it there, right? And then they assume the existence of these oracles that help you get it done. But again, that's not easy and definitely gonna require some more work. But there's another way we look at this as well. So it's hard to say exactly how this might work out, but in my opinion, it's entirely possible that there's a use case for quantum computers where they can also help you with the speed. So in high frequency trading or in low latency situations where, again, you need to come up with decisions super fast, with quantum computers, which again, some hardware devices work in microseconds scale, some work in millisecond scale. But the key thing to remember here is that in this microsecond scale, one layer of quantum operations actually corresponds to 2 to the 30 or 2 to the 100 operations in a classical computer, right? So you might be able to do operations on a quantum computer in order of microseconds that would take, again, minutes on a regular computer. And that might be where some of the use cases pop up, where they basically put a quantum computer on their high latency routes and use that as a fast decision maker. We're nowhere near that yet as of now, because again, the noise levels are super high and the calibration and all of data loading, state preparation, all of these things. But I can totally see that happening in next like 3 to 5 years.
Well, when it comes to democratizing quantum computing and making it have more widespread adoption, providing the tools to do it is one aspect of that. What are the other aspects that you see as being important to getting more widespread adoption of these technologies, getting industry and other sectors to say, yep, we've got to get on board with this?
Yeah, again, depends on the target audience that we want to attract, right? So if you talk about, for example, students and I don't know, high school students, then there's going to be more educational materials and more educational programs, which I believe is happening, and a lot of companies, including IBM, are working in that direction, and that's great to see. From the industry point of view, I feel like the first practical quantum advantage is going to be that first aha moment that will push a lot of companies to start opening quantum R&D departments, or actually start working with quantum companies to look into different use cases. What we see right now is a lot of companies, a lot of large corporations that have longer time horizons for their strategies, like 5, 10, 15 years, 15-year time horizons. These companies are already starting to look into quantum applications, right? But yeah, once we show practical quantum supremacy, then yeah, it's just gonna increase tenfold and hundredfold. So
becomes self-reinforcing the more utility it has.
Exactly, yeah. But it's going to be like the network effect and chicken and egg thing as well. It's going to attract more people. So people are going to look at more problems and find more use cases. So yeah, it's just going to be this virtuous cycle, basically.
Yes, absolutely.
Actually, to add on top of that, there's also the media and entertainment aspect that I feel like a lot of people in quantum community do not talk about enough, or talk in a negative way. I see a lot of people, again, from working in different quantum companies, who look at, say, movies or shows coming out of Netflix talking about quantum computing and criticizing them for the sake of like hyping the industry or claiming things that do not exist. But it's just a movie, right? It's just a show. That's his job, right? To kind of provocate and dramatize something. And in my view, it's perfectly natural, and it's great actually that we see like all kinds of movies like Quantum Mania, right? And there's like Netflix Black Mirror latest shows had some quantum computers in them. I look at those things and I'm just pretty excited to see how quantum computing is spilling into the mainstream. So yeah, I think it's a pretty positive thing.
How that evolves over time. In 10 years' time, the media might portray it very differently in Hollywood movies.
Do you mean like in a negative way, or more realistic way?
More accurate way.
Oh yeah, well, sure.
The one I like is called Lapsus, where it's not devoted to the tech at all. Really, it's about workers' rights, and about this guy who has to lay down cable for quantum communication interconnections between quantum computers, and they have to compete against robots. So it's like there's a workers' revolution that happens. It's a completely different.
Is it a new movie? I don't think I've heard about it.
Like 3 years actually, but it was a small screen release.
Oh, I see. 2017 Lapses.
Yeah.
Short movie. Cool. Yeah, I'm gonna check it out.
I feel like you're calling me out because I have a video on my YouTube channel where I watched the first episode of Devs, and I think I got through like 30 seconds of it before being like, okay, let's talk about the entire landscape of quantum security first. So yeah, I'm one of the bad guys on that one. But in general, I think I'm excited to see it presented in an optimistic light.
Yeah. Again, in Black Mirror, it's not really presented in the best possible way, right? It's like this evil machine that some corporations use to, sorry everyone, spoiler alert, but yeah, some evil corporation is using to, again, make a lot of money in at the expense of regular people. But yeah, it's just a movie. It's a fun scenario to fantasize about, and gives some idea about what quantum computers are, right? So I still think it's overall a positive thing.
Definitely. So, Hayk, thank you for coming on the Quantum State with us. So, last thing, how can interested parties get started with BlueQubit and make the most of your platform?
Yeah, so please, you can go to app.bluequbit.io, and there is an easy way to get started. And we have some docs and tutorials on what you can do on our platform. And we have some simple quantum programs, some quantum hello worlds, if you will, A+B program on how you can add numbers together on a quantum computer. So please check those out, and yeah, let us know if you have any questions.
Yes, thanks
Great.
so much. If you're watching this on YouTube, please comment down below so you can give us any feedback that you want about the episodes, about BlueQubit. We'll pass it on and hopefully revolutionize quantum computing together. So thank you, Peter, Gavin, for joining the Quantum State today, and Hayk, again, for talking so much about quantum computing and your vision for the future. So please like this episode, subscribe to the Quantum State, and join us next time.
Thank you for having me.